We're asked to rank the relative stability of some resonance structures. So the first step is to draw the resonance structures. We see that we have 8 electron pairs to distribute. And once we complete the octet of the outside atoms, we see the center atom is electron deficient by 2e pairs. So we're going to have to use the lone pairs on the outside atoms to create either 1 triple bond or 2 double bonds. So here are the structures of the 3 resonance structures. Okay, they're the same connectivity of the atoms. We'll have a triple bond on one side of the molecule here, maybe on the other side here in 3, and in the middle we'll have 2 single bonds. So this is 4 of our electron pairs. When we complete the octet again of our outside atoms, we can use our remaining electrons, so we have a total of 8e pairs in each of these structures. We'll go ahead and write the formal charge of each atom within each compound. Again, the formal charge is going to be the group number minus the non-bonding E's minus the bonds formed by that atom. First, there's no structure where all the formal charges are 0. So we go to the next rule, whereas +2 minus 2 is not preferred. And here we have that situation. Nitrogen here is -2, and we also have the situation where we have consecutive +1s. So we're very safe in concluding that this structure is the worst out of all 3. It's the least stable, and that also means it contributes least to the resonance hybrid. Okay, the only differences between structures 2 and 3 is where the -1 charge is. So if we look at structure 2, we see the -1 charge here is associated with a nitrogen, and structure 3, the -1 charge is associated with the oxygen. So we conclude that structure 3 is most preferred, most stable, because we have the -1 on the more electronegative atom. And therefore structure 2 is the next best, but it's not as good as structure 3.